Hi, welcome to Chapter 11, Liquids and Intermolecular Forces, Overview Part 2, where we're going to talk about some properties of liquids and phase changes. So, liquid properties affected by intermolecular forces. So, we previously discussed how the boiling point and melting point are affected by intermolecular forces. Remember, the stronger your intermolecular forces, the higher your boiling point. We're going to talk a little bit about viscosity, surface tension, and capillary action. So, intermolecular forces may affect many physical properties, and it's really because the strength of the attraction between the particles can greatly affect the properties of a substance or a solution. So, viscosity. Viscosity is the resistance of a liquid to flow. So the thicker your substance is, the slower it will flow. The slower it will flow, the higher the viscosity. So it's related to the ease with which the molecules can move past each other. So if it's hard for the molecules to move past each other, you have high viscosity. Think about honey. Honey is an example of something with high viscosity. Viscosity increases with strong intermolecular forces and decreases at higher temperatures. So if your forces between your molecules are pretty strong, it's going to be hard for something to move through it or hard for that liquid to flow. Okay, so it'll have a high viscosity. But as you raise the temperature, you're increasing the kinetic energy and you're kind of breaking some of the intermolecular forces, so you're reducing the viscosity. So if you look here in this data table, you see here we have hexane, heptane, octane, nonane, and decane. So they are progressively getting larger here and longer, so your intermolecular forces are increasing. So as you go down, your intermolecular forces are increasing. And look at your viscosity. As you go down, your viscosity is increasing. The next property we're going to talk about is surface tension. Surface tension is kind of interesting. And here we have a picture of this bug that is walking on water. This is sometimes called the Jesus bug. And it's using the surface tension to actually walk on the water. If you look closely around each part where it's touching the water, you see there's like these little lines or whatever, and that's really the surface tension. So what is surface tension? Water acts as if it has a skin on it due to the extra inward forces on its surface. So here you have water is attracted to itself, so it hydrogen bonds with other water molecules, and it kind of makes this skin on the surface. And here is the foot or the leg of the bug that kind of just stands on it. Okay, it causes water to beat up when in contact with a nonpolar surface. Okay, so if you ever have wax paper, you put a drop of water on it, it will beat up because water will hydrogen bond to itself and not the wax. So down here you see it beating up. Those forces are called surface tension. Surface tension results from a net inward force experienced by the molecules on the surface of a liquid. Okay, and this is why when you belly flop it hurts so much, because of the surface tension of the water. Let's go back. So if you have strong intermolecular forces, you're going to have high surface tension. And what would happen if you increase the temperature to your surface tension? So if you increase temperature, you're increasing kinetic energy, so you're going to break some intermolecular forces, so your surface tension will decrease at higher temperatures. The next properties we're going to talk about are cohesion and adhesion. Intermolecular forces that bind similar molecules to one another are cohesive forces. So if you have two similar molecules and they're sticking together, that's a cohesive force. So water, two water molecules, okay, sticking together, that's the cohesive force. Intermolecular forces that bind a substance to a surface is adhesive forces. So when you are measuring the volume of your water in a graduated cylinder and you form this meniscus, what happens is the water is attracted to the glass. With it, this here is your adhesive force. Because it's attracted to the glass, you form this meniscus. If water was not attracted to the glass, you'd have a straight line here. Or if it was actually repelled by it or didn't like it at all, you'd have the opposite of a meniscus. You'd have it kind of bowing up. So these two forces are important in capillary action. Capillary action, if you want to visualize it, put a drop of water on the counter and take a paper towel and just put the corner of the paper towel in that drop of water. And you will start to see the water traveling up the paper towel, and that is capillary action. The rise of a liquid up narrow tubes is called capillary action. Okay, so in capillary action, you're having adhesive forces and cohesive. So say your little tube that you want the water to flow up is made out of glass. So then, and your liquid is water. Water is attracted to the glass, so it will suck up the tube. Once some of the water goes up the tube, other water molecules like water molecules, so they'll follow. They will use cohesive forces to follow it up. So water has a strong adhesive force with glass, and that's why you get the downward meniscus here. Where mercury has a strong cohesive force with itself. It rather bond with itself than the glass. So when you look at it, you'll have this type of going on here. So if you look here, here is your glass. Here's your water molecule, and there's an adhesive force with the water molecule kind of sticking to the glass. Here is your mercury. It rather stick to itself than to the glass. That's why it's kind of bowing up, where this is bowing down. So this is kind of like this, bowing up. And this here is bowing like to make your meniscus. Okay, the next thing we're going to talk about are phase changes. So what are the 6 phase changes? Well, we have melting, and when you're melting, you start as a solid, and you end up as a liquid. Then we have freezing, which is the opposite. You start as a liquid, and you end up as a solid. Vaporizing, you start as a liquid, you end up as a gas. Condensing is the opposite. You start as a gas, you end up as a liquid. Sublimation, you start off as a solid, and you end up as a gas. And deposition is the opposite, gas to a solid. So which of these phase changes do you have to add energy into it in order for it to occur? Which are endothermic? Endothermic you're adding heat in order for the phase change to occur. So in this case, the endothermic ones are blue. So melting is endo, because you're solid, you have to add heat and then it will lift. Vaporizing is endo, and sublimation is endo. Okay, then you have exothermic, where you have to remove heat or heat is released. And they are written in red. What causes these phase changes to occur at the molecular level? It's kind of a tug-of-war between your average kinetic energy, which is the temperature, and the intermolecular forces between the particles. Okay, so say you're going from a solid to a liquid, you need to break some of those intermolecular forces. So you have to raise the temperature so you can increase the energy and break it. But say you're going from a liquid to a solid, you want to form more intermolecular forces. So you lower the temperature so you have less kinetic energy, so more intermolecular forces occur. So here is a energy diagram of phase changes. Remember, a phase change is a conversion of one state of matter to another. Okay, energy is either added or released in a phase change. And the phase changes that we mentioned before: melting, freezing, vaporizing, condensing, subliming, and depositing. So here you see the up arrows are your endo. So you're adding energy to these. And exo, energy is being released. So this is releasing. This is adding. And I kind of color-coded it like this, the previous slide. The blue ones are endothermic. You need to add energy to go from a solid to a liquid. You need to add energy to go from a liquid to a gas. And the red ones are exothermic. So these change of states, when you are changing from a solid to a liquid or a liquid to a solid, each of these changes has a certain heat that is associated with them. So the first heat we're going to talk about is the heat of fusion. This is the energy required to change a solid to a liquid. Okay, so if you're changing from a solid to a liquid, you have to add heat, and that heat is called delta H fusion. Or you could call it the enthalpy of fusion or the heat of fusion. Okay, then you have something called the heat of vaporization. So that would be delta H vaporization. And that could also be called the enthalpy of vaporization. This is the amount of energy you need to add to go from a liquid to a gas. And the last one is the heat of sublimation. And that is to go from a solid directly to a gas. Now, as it turns out, if you look at this graph here, your heat of fusion are the red ones. Your heat of vaporization are the green ones, and the blue ones. And the heat of sublimation are the green ones. So what do you notice? That your heat of fusion is always less than your heat of vaporization, which is always less than your heat of sublimation. Because let's think about this. When you are going from a solid to a liquid, you have to break some intermolecular forces, okay? When you're going from a liquid to a gas, you have to break all of the intermolecular forces in the liquid so that it can become a gas. When you're going from a solid to a gas, you need to break all of the intermolecular forces in the solid. Since they're in the solid, these intermolecular forces are stronger, and that's why it takes more energy. Okay? So here is a heating curve for water. This is for H2O. And you look here, here's this heat added, and that's your Q, and the temperature. And you notice down here your solid, liquid, gas. And so here your solid ice at -25, you're going to warm it up until it hits 0. Once it hits 0, it's going to melt. Notice the temperature does not change during a phase change. The temperature of a substance does not rise during a phase change. It does not change because all of the heat that you're adding is going into breaking the intermolecular forces. So it's not changing the kinetic energy, so the temperature is not changing. It's just going and breaking your intermolecular forces. Let me fix that F. It's bothering me. Okay, notice the length of BC compared to DE. BC is shorter than DE. So here, BC is your delta H fusion, and DE is your delta H vaporization. Now, on the last slide, we talked about this, and that for your heat of fusion, you have to break some intermolecular forces, not all. So you don't need to add quite as much heat. But if you're vaporizing, you need to break all. And that takes a significantly more amount of heat to do. And that's why this line is longer, because you need to add more energy to go from a liquid to a gas, because you're breaking all of the intermolecular forces. When you're going from a solid to a liquid, you have to break some, just enough to get the particles to flow over each other. So how do we use this graph to actually calculate the amount of heat? So how would you determine the amount of heat required to heat a quantity of water? What equations would you use? Now, I know in your sophomore year of chemistry, your teacher spent quite a bit of time on this. Maybe you remember it. The regions here that have a change in temperature, so the blue ones, the blue regions, which would be A, B, C, D, and E, F, all will use Q equals MC delta T, which we used earlier this year, where M is the mass in grams, C is your specific heat, delta T is your change in temperature, and Q is your heat energy. All of the red lines, which would be BC and DE, the temperature is not changing. So you can't use this equation because your delta T would be 0. So you have to use Q equals N delta H, where your delta H could be delta H of fusion or your delta H of vaporization, depending on what region you're in, okay? And N is moles. You have to be careful. Your delta H is normally given in kilojoules per mole. And when you calculate that your Q here, you're normally going to get Q in joules. So because we need to add the two together, you have to convert this to kilojoules. And for water, each blue line here has a specific heat value that is different depending on the state. So your specific heat of the solid, so we'll call that CS parentheses for solid, is 2.09. Your specific heat of the liquid is 4.18. And your specific heat of the gas is 1.84. So just by looking at this, your water has a higher specific heat, so it'll take longer for it to warm up. And if you kind of compare the slopes here, AB is steeper because it'll warm up, ice cubes will warm up faster than, say, your water. Your enthalpy of fusion, which is your delta H fusion, is 6.01 kilojoules per mole. And your enthalpy of vaporization, which is delta H vaporization, is 40.67. Notice this number is significantly larger than this number. And this length is also significantly larger because, again, in your heat of vaporization, you are breaking all of your intermolecular forces. So how do we go about solving this? So it depends on where you're starting and where you're ending. So here it says, given the following constants on the previous slide, determine the energy required to raise the temperature of 20 grams of ice from negative 40. So this graph only goes down to negative 25, but let's assume we're down here, negative 40 to steam at 120. So we have to calculate Q for all of these regions. So we're going to have Q1, Q2, Q3, Q4, Q5. So there are 5 steps to calculate this. So the first step is to take your cold ice and warm it up to 0. So you use Q equals MC of the solid times your change in temperature. Your change in temperature is going from -40 to 0 because this equation here is only good up to 0. Once you hit 0, then you are melting. So you're going to use a different equation, okay? Even though the temperature range they give you is -40 to 120, you can't put 120 in your delta T here because this equation, Q1, is only good up to 0. And then you calculate your Q value. Then next we're going to have to melt it. So we have to take our 20 grams and convert it to moles by dividing it by the molar mass of water and multiplying it by the delta H of fusion. And we get our Q for that. Next, we're starting here at 0 degrees C and we're ending here at 100. So here is our liquid. So we use Q, C of our liquid, times our delta T. So here's our mass. C of the liquid's 4.18. And what is my delta T? Well, this Q equation is only good from 0 to 100. So my change in temperature is 100. Then I do Q of the vaporization. So I use N times delta H vapor. Again, I have to convert it to moles. And I get my Q for that. And last but not least, I'm going to take my gas at 100 and warm it up to 120. So my change in temperature here is 120 minus 100 because that is the region that I'm in. So my change in temperature is 20 because you do 120 minus 100. Calculate that. Then you add all of them up and that gives you your total heat to raise 20 grams of ice at -40 to 120 degrees Celsius. The last thing we're going to talk about are supercritical fluids. So gases liquefy when pressure is applied to them. But the temperature beyond which a gas cannot be compressed is called the critical temperature. So that means that if you are at a temperature higher than this critical temperature, you cannot squeeze your gas into a liquid. It cannot be compressed. Okay? And the pressure that needs to compress the liquid at the critical, so this temperature, when you're at the critical temperature, you can still squeeze it, and the amount you have to squeeze it is the critical pressure in order to get it to be a liquid. Okay? But if you are beyond the critical pressure and critical temperature, then there's nothing you could do to that substance to get it to liquefy. So the state beyond the temperature, or beyond your critical temperature, is called a supercritical fluid. Okay? So very high temperatures, very high kinetic energy. There is not enough pressure you could do to get it to actually become a liquid. It's kind of a high energy gas. And this critical temperature depends on your intermolecular forces. The stronger your intermolecular force, the higher your critical temperature. And you can kind of see that here because nitrogen is a nonpolar gas and its critical temperature is 126. Water, hydrogen bonding, its critical temperature is 647. Okay? So, higher intermolecular force, higher critical temperature. And that is the end of overview part 2.